Section 1.2 is about computing the average rate of change of a function. And then we're going to talk about how that relates to the slope of a line, and then how to find the slope-intercept form of the line and the intercepts of a linear function. All right. So the topic of linear equations should be familiar to students starting intermediate algebra. The basics are covered here with reminders of important ideas and concepts that will be heavily utilized in the next lesson. So we're going to talk about these things, these two topics, or the topic of lines, a lot in Unit 1. Pretty much all of Unit 1 is about lines. So keep that in mind. This nice gray table here, slope versus average rate of change. The slope is denoted by the letter M. And if you're given any 2 points, x1, y1, and x2, y2, the slope between those 2 points is given by the change in the output over the change in the input. What does that mean? So we want to find the difference between the outputs, or the difference of the y's, divide that by the difference of the input, or the difference of the x's. We get the formula y2 minus y1 over x2 minus x1. You'll see this notation delta a lot, the little triangle. Delta output means the change in the output. Delta input means change in the input. And then when we're dealing with linear functions, basically calculating the average rate of change is the same as finding the slope. The only difference is the slope just it's represented by just a number. When we calculate an average rate of change, we should also include units to explain what the numerator and denominator represents. So you might have like, oh, the slope is 1/2, but in an application problem, that 1/2 would represent the change in output over the change in input. So if the input is the number of credits and the output is the cost or something like that, that would be then the cost increases by 1 and the output increases by 2, or sorry, the input increases by 2, the number of credits. Or an easier way to think about this is when you're writing out your slopes or your average rate of change for linear functions, always remember that the output units go in the numerator and the input units go in the denominator. And when you write out your final answer, it should be the slope, and then you should have the units being output over input. So if it's dollars over credits, or dollars over time, or distance over time, always output over input. All right, the denominator of the average rate of change is always 1 unit. Units are read as output units per input unit. Problem number 1 is a worked out example for us. In New Jersey, the average gas price in January 2020 was $2.64. The good old days. In June 2020, well, those are kind of the bad old days, June 2020, but gas got cheaper because nobody was going anywhere. It was $1.99. Determine the average rate of change in the cost of gas from January to June using the correct units. State the practical meaning. So we want, if we look at this, we're comparing the price of gas to the month. If you pick a month, we can tell you what the price of gas was at that time, right? So the month is the input, the price of the gas is the output. So when we calculate our average rate of change, it would be change in the price of gas over the change in months, okay? I don't like these numbers, but that's fine. When we look at January and 2.64, June and 1.99, we can create ordered pairs for that by corresponding January to the number 1 and June to the number 6. So that gives us the ordered pairs 1, 2.64 and 6, 1.99. The input is the month, the output is the price of gas. When we compute the average rate of change, y2 minus y1 over x2 minus x1, we can see that 199 minus 264 gives us negative 0.65. So the price of gas went down by 65 cents over how much time? From January to June, that's over those 5 months. Over a 5-month period, we got a decrease of 65 cents. So what is the average rate of change? If we divide 65 by 5, that gives us negative $0.13 per month. What does that mean? On average, from January to June, the price of gas decreased by 13 cents per month. Sorry. I know that it's decreasing because the average rate of change is negative. And then that 13 just represents the decrease per month on average. In real life, did the gas go down exactly 13 cents per month? No. It probably jumped around a little bit, but this just gives us an average number that we can use to kind of estimate what was going on at that time. Problem number 2 is a guided example for us. In the table below, we see the distance covered by Daniel during 6 weeks of cardio exercise. So our good friend Daniel started working out, doing cardio for 6 weeks. At the top of this table, we see the weeks. And then at the bottom, we see the distance that he's running. I guess he's running, doing cardio in miles, okay? So in week 0, Daniel did 10 miles. For week 1, 12 miles, week 2, 15 miles, week 3, 16 miles, and so on, okay? We are asked, what is the average rate of change covered by Daniel from weeks 0 to 4? Week 0 to week 4. All right, so in order to do this, we want to look at the ordered pair associated with week 0, that's 0, 10, and look at the ordered pair associated with week 4, 4, 14. And then we want to compute the slope between those two numbers. But don't forget, since we're asked for an average rate of change, we also want to include the units in the numerator and denominator. So this is going to be the change in the output, the distance, over the change in the input, the number of weeks, okay? The numbers that were given, week 4 to week 0, for the distance would be 14 minus 10. That's miles. Over the weeks went from 4 to 0, or 0 to 4. 4 minus 0 weeks. All right, subtracting here. 14 minus 10 is 4. So that's 4 miles over 4 weeks. And then we want to simplify the numerical part. 4 divided by 4 is 1. So that's 1 mile over week or per week. What does this mean? So this is saying that Daniel's distance increased by 1 mile each week, right? 1 mile represents the change in the output, which is the change in the distance, and then per each week, all right? So the distance Daniel covers increases. We know that this is increasing because the average rate of change is positive, on average by 1 mile per week, 1 mile per week in the first 4 weeks. All right, we're going to do the same type of calculation for part B, but for different weeks. Instead of looking at weeks 0 to 4, we're going to look at weeks 3 to 6. Week 3 gives us the ordered pair 3:16. Week 6 gives us the ordered pair 6:13. All right, so how is his distance changing over the weeks from week 3 to week 6? Let's compare that. Delta, kind of scroll up a little bit here. All right, delta D over delta W would be 13 minus 16 miles over 6 minus 3 weeks. So that's what? -3 miles over 3 weeks, which simplifies to -1 mile per week. So between weeks 3 and 6, it actually looks like the number of miles that Daniel runs or does cardio for is decreasing by 1 mile per week. So the distance Daniel covers decreases on average by 1 mile per week. Notice that I said that it decreased by 1 mile, not decreased by -1 mile. Saying that it's decreasing takes care of the negative. And then we want to explain how much it's decreasing by. It's decreasing by 1 mile each week. And remember, this just gives us an average to kind of explain what's going on in those weeks. It's not exact, but it gives us a number that summarizes what's happening. We're going to go to number 5, which is a guided example. Function versus a linear function, and the slope versus the average rate of change. After completing a 4-year college, Huiku has a student loan debt of $32,830. He plans to reduce this debt by at least $2,345 each year. Use the given information to complete the table below. So in year 0, he's starting off with $32,830 in debt, okay? Each year, he's going to decrease it by $2,345. So we can subtract that amount for each year. So $32,830, and then if we subtract $2,345, after 1 year, he's down to $30,485 in debt. After 2 years, he's down to $28,140 in debt. And then after 4 years, we have to subtract 2 times. I got $23,450. After 6 years, $18,760. And after 9 years, his debt will be down to $11,725. Okay. So use the given information below to complete the table. We did that. Is the remaining loan debt a function of the number of years of payments? Why or why not? When you're asked that, you want to ask yourself the question, does the remaining debt depend on the number of years of payment? Yes. And does each year correspond to exactly one amount of debt remaining? And the answer is yes. So yes, because, oops, why can I spell each today? Each year corresponds to one remaining balance. That's the definition of a function. Each input goes to one output. Okay, that's part B. For part C, what's the input and the output? The input would be the number of years, and the output would be the remaining debt in dollars. Okay, you pick the number of years of payment, we can figure out what the remaining debt is. All right, and then part D. Choose 2 sets of ordered pairs from the table above and determine their average rate of change for each set. State the units and state the observations about the results. So let's pick 2 different pairs. Let's say we look at years 0 to 1 and then maybe 4 to 6. And we're going to calculate the average rate of change. So we're going to go n equals 0 to n equals 1. And then over here, n equals 4 to n equals 6. And we did these calculations in the last example. So the same way we computed the average rate of change when we were given tables previously, we'll do that now. Just gotta make sure I can see all my numbers. So for the first one, we're gonna have delta R, that's the remaining balance, over delta N, the number of months. Number of years of payment. I know the years are going to be 1 minus 0 years. And I can't remember the numbers for the debt because I am forgetful. Okay, so it would be $30,485 minus $32,830. All right, when we subtract this, the difference is going to be equal to negative $2,345 over 1 year. So from years 0 to 1, the average rate of change of the remaining debt is, it goes down by $2,345 over that year. All right, now we're going to use the same calculation but with different numbers because we're going to look at n equals 4 and n equals 6 for the next one. Our numerator would be the change in the balance. So $18,760 minus $23,450, and then over 6 minus 4 years. All right, let's calculate that. 18,760 minus 2,3,450. That's negative $4,690 over 2 years. And if we divide this by 2, ta-da, gives us actually the same thing, negative $2,345 per year. So if you refer back to the previous examples we did in this problem where we were looking at average rates of change, for most of them, for all of them in this chapter, or in this section, when we computed average rates of change for different ordered pairs, we ended up with different average rates of change. However, in this case, we picked 2 different pairs and we got the same average rate of change. Actually, if you pick any 2 ordered pairs here and calculate the average rate of change, you would get the exact same number every time, okay? This is a very special case where we have a constant average rate of change, okay? What is the practical meaning of the average rate of change? So negative $2,345 per year means that each year, the remaining balance decreases, because it's negative, by, how much is it decreasing by? $2,345. All right, now again, this is a very special case where it doesn't matter what 2 ordered pairs you pick, you end up getting the same average rate of change. And that's because we were told in the beginning that each year we're decreasing by the exact same amount. So we have a constant average rate of change. Problems like this, where the function has the same average rate of change, represent linear functions. So if you have a table and for any ordered pair any 2 ordered pairs you pick, the average rate of change comes out to be exactly the same number every time. That means that the average rate of change is constant, and that represents a linear function. And then we can take it a step even farther. Whatever we get for that average rate of change gives us the slope of the line. So for linear functions, the average rate of change is constant, and the average rate of change is the same thing as the slope. Things we know about lines and slopes. Some of these average rates of change have been positive and some have been negative. When you have a positive average rate of change that represents an increasing function, the graph rises from left to right. When you have a negative slope or average rate of change, that's a decreasing graph. If you get a graph where the slope is 0, that means it's constant, it's not going up or down. You get a horizontal line. And it is also possible for you to get a graph where the slope is undefined. That means the x values are the same. Then that gives you a vertical line. All right, so problem 6 is just saying that, hey, what we did in problem 5, where we found that the average rate of change was constant, that represents a linear function. So what type of function? Linear, because the average rate of change is constant. Okay, and is the function increasing, decreasing, or constant? Remember, the debt was decreasing by $2,345, and that means that the slope is negative. This would be a decreasing function. And then what are the differences and similarities between slope and average rate of change? The average rate of change does not have to be constant. It can be any number. It can be positive or negative. Average rate of change also has units. The slope is just a numerical number. And if the average rate of change is constant, it's the same as the slope for the line. Okay. Now that we know that constant average rate of change gives us the slope of our line, we can use that. We can talk about graphing lines. If we're given a graph, we can find the line. We'll talk a little bit more about horizontal lines and vertical lines as well. Next, we're going to look at a graph. This table gives you some information about what a good graph should look like. Your graph should have a title. Your graph should have labels on the horizontal and vertical axes. And your graph should have a scale, okay? Start at or just below the lowest value and end at or just above the highest value for your X and Y, okay? Oh, anytime you draw a graph for this class, it needs to be accurately drawn. You have to have a title, you have to have labels, and your points need to be identified in order to get full credit, so keep that in mind. For number 7, it says use the information from problem 5 to graph the line on a set of axes below and show all labels as described above. So in problem 5, we never actually wrote out the equation of the line, but we can. This is the information that we're given. 1, we can all agree that we've calculated and determined that the slope was negative 2,345. Okay, I hope we all agree with that. The other bit of information we would need is the y-intercept, which is given here. We start off with $32,830 in debt, and then every year it goes down by $2,345. So we'll put that together to write out the equation. All right, so from 5, our function would be R of n equals negative 2,345n plus, what was it, $32,830? $32,830. Oh, my mind is going. I got to go and check again. Yes, that's the right number. All right, so when we graph this, the input should be on the horizontal axis, the output on the vertical axis. So this would be the N, the number of years, and this would be R, the remaining balance. I'll just put balance. And then for our scale, the years are going up by 1, so that's not too bad. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But for the y-axis, we start off with the balance of a little bit more than $32,000, and then it's decreasing eventually to go down to 0. Each of these tick marks can't represent $1. We don't have enough tick marks, or $10 or $100. We have to think of what would be a good number to represent each tick mark by. We can go by, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I said we can go by 4,000s, okay? So if that's 4,000, 8,000, 12,000, 16,000, 20,000, 24,000. Did I skip one? Forgot how to count by 4s for a second. No, believe me, 28,000 and then 32,000. That could work. Okay, that's one way you can write this out. Or maybe you don't want to go by 4,000s. I want to point out this one important thing that's here. Eventually it will go down to 0, but in our table, we are not given values that go all the way down to 0. So it might take us a while to get there. So between 0 and 9 for our input, we're going to go from 32,000 to about 11,000 for our outputs. If you want to only show those values, sorry for all the scrolling back and forth, we can also use 2 dashed lines to indicate that we're doing a big jump. So we know that the origin is 0, 0, but then we're doing a big jump. And you can say, oh, well, this is 11,000, and then, I don't know, 11, 13, 15, 17, 19, 21. That might work. 11,000, 13,000, 15,000, 17,000, 19,000, 21,000, 23,000, so on and so forth. The moral of this story is there are a couple of different ways that you can label your axes. You want to try to use the information given to you in your table though for your inputs and your outputs. The inputs will help you label your horizontal axis. That one was easy. The outputs help you label your vertical axis. And if the outputs don't go all the way down to 0, you can use this little dashed line to indicate that there's going to be a little bit of a jump. All right, we need to at least have 11,000 down here. We need to get all the way up to 30,000. So let's do the best we can, or 32,000. I'm going to go up by 3,000. That should work. So 11, 14, 17, 20,000, 23,000, 26,000, 29,000, 32,000. And again, if you label this slightly differently, that's okay. It could still work. All right, plotting our points. We can plot. The first number was 0, $32,800. So that'll be about here. And then we have 1, $30,485. That would be about here. And then we had 2, $28,140. That would be about here. Then next we had 4, $23,450. That would be about here. 6, $18,760. 6, 18, that'll be about here. And then 9, $11,775, or $725, which would be about right there. All right, then if we put all of these points together, eventually it will go to the bottom. We will get a good graph. Ta-da! It's labeled. You can also pick a couple points here to label on your graph. For instance, this one's 4, 23,450. You can label a couple of them. All right, that's all we were asked to do in problem 7. Then on to problem number 8, which asks us about the vertical intercept, and then we'll stop at horizontal intercept. From the table in problem 5, in the graph, what was the vertical intercept? We saw that the vertical intercept was 0, $32,830. That's the initial amount of debt that we started with. What is the practical meaning? The initial remaining balance is $32,830. Or you can say something like, this person starts off with $32,830 in debt. All right, part B, the vertical intercept is the ordered pair 0, B. The value of B is the output that results when we have an input of 0. And this is sometimes called the y-intercept as well. If you have the slope and if you have the y-intercept, you can put those two things together to find the slope-intercept form of a line. Y equals mx plus b. This is important, write it down. In this line, B represents the y-intercept and M represents the slope. And if you have those two things, you can write the equation of any line. At problem 10, we're given a bunch of equations in slope-intercept form, linear equations. We have to identify the slope and identify the vertical intercept for them. So for the first one, y equals -2x plus 5. That's already in slope-intercept form. The slope is the number in front of the x. So m is -2. That means the line is decreasing. And then the vertical intercept is given by the constant 5. That would be the ordered pair 0, 5. All right, for part B, y equals 2 minus x. This one, the order is switched. If we write this in slope-intercept form, it would be y equals -x plus 2. And then here, it's a little clearer to see that the slope m is -1. Again, this would be a decreasing line. And we have a plus 2, so the vertical intercept is 0, 2. All right, for part C, y equals 3 over 4x plus 2. Where are we? Okay, y equals 3 over 4x plus 2. That's already in slope-intercept form. The slope here is 3/4. That's positive, so we have an increasing line. And the ordered pair here will again be 0, 2. For part D, this is in slope-intercept form. Y equals 4x is the same as 4x plus 0. The slope is 4, so it's increasing. And since there is no constant there, that means it crosses at the origin. The y-intercept would be 0, 0. All right. Part E is interesting. Y equals -6. There is no slope, or the slope is 0 in this case. So this is the same as y equals 0x minus 6. M is equal to 0. So it's not increasing or decreasing. We have a horizontal line. And our y-intercept is 0, -6. And last one, this is the identity function, y equals x. So that's the same as y equals 1x plus 0. The slope is 1. It's increasing. And 0, 0 is the y-intercept again.